welcome to part 2. I mean part 1. I start counting at 0 like a proper human. So welcome to part 1 of my vlogging series on writing a virtual tabletop RPG system or something else. We'll see later. But for now, that's the plan. I finished porting over the ECS system from a couple of different projects, patched it together from different variants, and that was a mess. It's now much cleaner, and I'm nearly happy with it. There's a lot to do still, obviously, but that is more or less done. I will go over more specifics and code in it because it's very isolated, which makes it easy to look at. And I should also explain what an ECS system is and why we're using it, or at least plan to use it. Maybe I decide later that that was a mistake. In software engineering, there are typically two ways, I say typically because there are more, ways of designing your application and structuring it. Typically, when we have a thing, we need some way of deciding what can be done with that thing or what that thing is. In object-oriented design, the paradigm most of you are probably familiar with is to do this through class labels, typically. It's a bit more complicated because objects and it depends on definitions, but typically the very standard example people learn is, for example, an animal hierarchy, that you have a cat that is an animal, that is an organism or something like that. And that's in a class hierarchy. In the context of something like a game, it's easier to think about a class, for example, called character. And then underneath that, you have a player, you have, for example, an NPC, and maybe you have an hostile NPC, or you have an archer, ranger, rogue, etc. These kind of things. That is one way of structuring it. Another way of structuring is to look at the data they have, and the data decides what they are, and what is way more importantly, what you can do with it. If we go back to the game example, because it's easier there, an archer could be defined as something that has a stat block of an NPC and has a ranged attack, and maybe is hostile. So you would look at these three components and say, that is a hostile archer. The advantage of this is that if someone, for example, converts their class somehow, you turn from an archer into a knight. If that is modeled as a class hierarchy, that's a problem. In nominal type systems, you typically can't change your class. You can by casting upwards usually, and sometimes downwards, but you can't switch branches in your hierarchy tree. And there is no good solution to that. One could model it differently and have a character have a field in it or a property of it, which is class, which you can then replace with a different one. That is a composition-based approach, which comes very close to data-based or database modeling. And in the case of what I earlier discussed about the database approach, if you simply remove the archery part from him and add the, I don't know, sword to him, automatically he gains the abilities of someone that can use a sword and loses the ability of someone that uses a bow. And that's very simple. And that's exactly what an entity component system is. It gives us some sort of an ID we can associate data with, and then we define systems that manipulate these IDs based on what kinds of components they have. This was probably a very scuffed explanation. Sorry, I don't have a script. I'm just doing this ad hoc. Let's look at some code. Oh, no, let's look at some code. The central theme of an entity component system is the entity. The entity is nothing more than just an ID. It just tells us that something exists. I have generations in here because I'm reusing IDs. We're gonna see that in a second, how that works. For performance reasons in how I manage my components, I want to keep the ID number that I'm using relatively small. It's simple. We have one flat list. That is as long as many IDs we have. The highest ID we have. Sorry. As many IDs that have ever existed, that is how long generation is. And 3 indices or 3 IDs just carries a deck of IDs that currently are not in use. It's a deck because I'm cycling IDs, because as one ID gets freed up, its generation increases, and by always cycling in the oldest unused ID, I keep the generations balanced, which means I don't get some weird artifacts where something runs away with its generation while everything else remains low, which could be relevant in some very exotic edge cases. Theoretically, we can overflow here. I don't know if I care because it takes billions of iterations for that. And any normal functioning system should not be generating these entities and dropping them that fast. But since the generation has to match, I could just reset the generation to 0 and make sure that nothing has a generation of 0. Maybe have a... No, that doesn't work. Anyway, moving on. When we create a ID, we just check if we have a free index. If we have an index, we grab it and we grab its associated generation. If we don't have one, then we create a new one, add its generation 0 to it, and return that. Despawn, we just check it. If it's alive, we increase the generation, meaning that anything that points as this ID is now not alive anymore. And then we put the ID to the back. As you can see, we popped it from the front in spawn, and we're pushing it to the back in despawn. Is alive just checks if the generation, if this is an ID that reasonably came from us. If you have multiple entity management systems, that is a problem, because you can pass them around. Maybe I want to include some safeguard against that by including some random number, cryptographic random number potentially, in the entity that denotes the entity manager it came from. Or I force some other entity management system that attaches labels to them. Either way, it simply checks if a generation if the known generation of it corresponds to the entity generation. So we know that this actually just makes the old one invalid. That is really all there is to say about an entity. The world itself is a bit more interesting. It holds the entity manager. So you're never supposed to directly access the entity manager, and that is guarded by the world. You can still create entities outside of it by manually creating it, but you can't guard against every stupidity of the user, which in this case is me. Anyway, we keep the components by type ID. So in Rust, once you compile the application, there are no struct names anymore. There are no traits. They all disappear. Or at least no concrete types anymore. And the type ID is a compile time constant that denotes which type it came from. And per assembly, that is unique. But between compilations, it can be different. So it is unsuitable for serialization, for example. But as long as the application is running, it is perfectly suitable to use. Anyway, for every type of component, we have some sort of storage of components. Resources are global components that are attached to the world directly. We can also name them. That allows us to have the same component multiple times with different names as a resource. We have indexes, which is typically not something you see with ECSs, but that is useful, for example, if you have a spell with an area of effect. And instead of going through every possible thing that could be affected by this, we can just query a spatial thing and say, give me everything that is around the center of the spell impact, and only process these specific entities. That's what the indices are for. And component tags are just a convenient thing. We don't really care about them yet, or for a very long time, probably. We can register storage, and that is the way I'm storing things is currently in a sparse storage system, but I wanted to decouple that, and you can technically use any type of storage you want. We'll look at storage in a second, as long as it fulfills the contract. But you need to register it beforehand, before you use the first component of that type. I could extend it so that you can overwrite the storage and then pull all the components out of one storage, push them into the new one, and update it that way. Maybe I will do that. Because there currently is also no way of removing them. It might be interesting to dynamically determine a different type of storage based on behaviors, runtime behaviors, but I don't think it's a reasonable thing. You probably register your storages once at startup, basically, and leave it at that. Spawn, despawn, only extra thing. Despawn also cleans it out of the components. It cleans up the indices and it cleans up the tags. Indexes can also be added at runtime at any point in time. It comes from an index builder, which allows us to instantiate it from a set of data. Because Rust, you cannot have in trade. To make a trade dinnable or dynamic, it needs to be able to always build a vtable. That means all functions basically have to have a reference to self. And build with data does not have a reference to self because that is supposed to be a factory or a constructor or whatever you want to call it. Which is why it takes a builder instead. And some index structures are way more efficient to generate from the set of data. For example, a binary tree you can generate from the sorted list extremely efficiently. That's why it's here, because you can add them theoretically at runtime, so you might already have a lot of data. I don't use any efficient ways of building them, so it doesn't really matter at this point, but it's there. Right. This is a bit intrusive. I'm not sure I like this. For the world to go and fiddle out the generation. Maybe I want to, instead of just storing the ID raw, have that somewhere else, or have a lookup method in the world to do this. But since I'm single-threaded, technically I know that this is still valid, because if it is inside the world, then it didn't despawn yet, which means it should have, this generation should match. That's it. And then I just store the index. We can get the index. There's no way of removing indexes, which maybe should be a thing. If we add a component, if the entity is not alive, we don't care. Otherwise, we add it to the index, and we add it to the corresponding storage. And if we did not register a storage for it, then we're going to use a sparse set. That just allows us to do some things very efficiently as long as our ID at the cost of memory. So as long as we don't have very large IDs, this is good. A very efficient way of doing it. Then we can get the component of a specific type for an entity. We can remove a component of a specific type from an entity, which it always cleans it up from all three places. Resources are the same thing, just on the world level. And then querying becomes more interesting because that is what allows our system to actually work. And we can query for a specific component. We can query for all entities that have a specific component. And for that, we just grab the storage of that type here, and just grab all the entities, and then we fiddle this out again. Again, I don't really like that we are doing this. Maybe it makes more sense to just store the entities with their generation included in the components. I'll consider that. And that's what we return. Otherwise, we return the just the vector, the empty vector. Then we can query entities that have a set of components. And here we're going through, we're grabbing every single storage, if it exists for that component. If some component doesn't exist, then we know that the intersection is 0. So we can just return that. Anyway, we're just sticking them in here, and then we sort them by their length because it's more efficient to go through the smallest one. This is highly inefficient because entities returns a slice. And it might make more sense to return here a hash set of some sort or some other structure that allows us to index them fast, do this filtering fast. We could, for example, enforce that they are always in sequence, so sorted ascending. That will also allow us to very efficiently cycle through them and build our entities from it. But this is the way it is right now. I'll deal with it at some point of time. Then we can also grab all components that belong to an entity, which is just iterate through every storage and grab the entity from it. The type ID. We don't actually grab the component. Tagging is not that interesting. And that is it. If we look at a storage, that is basically just a trait. If you work with ANYs and Rust, which is the only way of escaping the type system or the strict typing and allowing you to store dynamic things where you don't know the type of at all, and especially the only way of downcasting is specifically on the any trait. I believe I have a video on this. I'm not sure. Maybe I should make one if I don't have one. Anyway, any is anything that has data like this, where you store arbitrary types, will have these two functions basically on it. At least in my code, and I'm sure in everyone else's code as well. This is a very common pattern. Anyway, storage allows us to remove the component that belongs to an entity. It allows to check if an entity exists. If a component for that entity exists, it'll allow you to get just all entities from it. To insert an component for an entity, to get the component for an entity, to get it mutably, and to remove any and to remove the entity from it. that also returns the component. Sorry, I got confused why I have both of them. I am confused why I have both of them. I don't really need both of them. It doesn't matter. I'm not sure I like the ability to get it mut at all, because that can mess with the indexes. Do I allow in the world? I don't think I allow the world to return it mutably. No. Sorry. Get component. Yeah, I don't have a get component mode. But you can still bypass it with interior mutability. So maybe instead of an option, I want to have something that a sort of smart pointer my own that detects the drop and then on the drop updates the index. I don't know. It's interior mutability makes stuff always difficult. Which theoretically Rust is supposed to be safe against, but then that hack exists. Anyway, sparse set, it just has as many slots as there are IDs, or at least the highest ID it ever saw. The dense is the actual IDs. So let's say ID, we have a component stored for ID 2 and 3 and 0. Then this vector would be 0, or would be sum, none, none, sum. And in here, they would be without the nuns. This is faster because we can return a slice to dense immediately. And we can find the entry in dense immediately through the sparse one, because that is just the ID of, sorry, the index of the entity itself corresponds to the index of the data and the dense one. So we can just do it with one lookup, find exactly where it is. But this list needs to be as long as the highest ID we saw, which is why I said we want to keep that number relatively small if we can. For the sparse set, but that's also why we can register a different index. Yeah, and then it just supports inserting. Inserting just means we're checking if the index is larger than the largest known one. If it is, we resize the thing, and then we stick it at the correct spot, which is simply the entity ID is the correct spot, but the dense one is whatever this one pointed to from the sparse one. And we replace the component with it if it already exists. That is the component override. If a component did not exist, so there is no entry in sparse, then we're going to swap the components around. And that is, we're going to look at sorry, not swap. We're just going to push it to the back. I don't know why I said swap. We're swapping on delete. We're just pushing them to the back. We just get the new end of it and update the thing. We look at the delete in a second. Get is relatively uninteresting. We simply grab the index from the sparse one. If it exists, then we grab the data out of it. Get mute is the exact same thing. And remove is the thing I wanted to say with the swapping. And that is, we find the entry in dense that the sparse one points to, and we swap that one with the last one, which allows us to just pop from the end of it, which is very efficient. Because removing an entry from the middle of an array or a vector, which uses arrays underneath, requires that you shift all elements to the left afterwards, which can be very expensive for a larger one, whereas this is doesn't do anything actually, because Rust does not shrink arrays dynamically or vectors dynamically. They stay the same size unless you tell them to shrink. So this pop just shifts a pointer. This is super cheap. And mem swapping is a mem copy operation, which is also super fast. Yeah, that's one way of, if you don't care about the order of deleting an item really fast, is to swap it with the last one and popping the last one off. Contains just checks for contains, and then this is just implemented and just points at the elements. A system is potentially interesting, but it's really just something that takes in the world as an argument and then works. We saw an example in here. Did we see something? I don't know. But for example, a system that would be update movement of things based on their velocity. So you would query for all entities that have a position and a velocity. And then for all of them, you would update the component. And you can see here the exact issue I was talking about. If this was a spatial index over their actual position, that index would be wrong now. I don't think I have a get component mode. Why did I write that? I don't remember writing the get component mode in here. That must have been by the LLM. I asked it to just cross-link things and it changed things everywhere, which is super annoying. Unwrap.clone. There we go. Oh, wow. It just fucked up everything. Because you can remain this way. And then we can do a word dot. Add component. Oh, come on. I can just do the entity and then we pause like so. Because this will update the index actually. I need to double check everything now. Whatever. If I returned a mode one here, I would need to have a pointer that detects when mode goes out of scope so that I can then update the indexes. Because when you borrow it mute, you can assume they wanted to actually modify it. Or I need to trust the user to update the index, which I will not trust them because they don't necessarily. Not every system knows which which indexes exist. So, yeah, that's all a system is. It just has a run function. The name here is just for uniquely identifying them. I want to use a dependency graph at some point of time so that you can say a certain system has to run before a different one. And then there are indexes, which I don't really want to go into because I already talked about how R trees and B trees work. And yeah, but I haven't talked about how you would use an index. I believe I wrote an example in here. I did not. No matter, I wrote an example in the tests, actually. I actually wrote tests for this. Da, 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 da. Test removal, register, index. Yeah. So you would just query the specific index you want. If the index exists or not, you need to know. You probably shouldn't just blindly unwrap it because that's an error. But if the index exists, then you can do your query here. And in this case, it queries everything between 5 and 15. And that is on the X level. So you could also use two non-spatial indexes to model a spatial index, but that would be relatively inefficient and you would need to do an intersection between those two sets. Anyway, you also need to add the index through the index builder here. And the index gets an extraction function, which tells it how to get the index key out of the object itself. Yep, that's it. I believe deleting the entity is not the most efficient. But we know that the entity can only show up in the tree at most once. So it is efficient enough. If it could show up multiple times, that would be a problem. But we have no good way of finding the entity. We really should, for removing the entity, also provide the component so that it can go and find it based on the old component. And we should do that. Oh, let me check that. Do we do that on, how does update work? It just grabs the new component, huh? Oh no, I was intelligent and sorry, it's been a while since I wrote these. I ported them over. I forgot that I stuck a lookup map in here. That is what I wanted to say, that I may want to do that. Specifically this, add a lookup map for the remover, so that we can access what the old value was, use the extraction function on it to find the thing. And that is where mud gets in the way again. So I really do not want to expose them as mud. At all. There we have the answer. And I think you have the same thing, yeah. Why did I split this? I did that earlier, but... Oh, that's why I stuck the node. Why did I put it over here? Instead of just to the... I don't know. I do not know why I put the node over here, not... That was the structure I had in a previous project. Okay. Anyway, I will possibly clean that up still. But with an ECS system, with a basic UI, with the ability to render things, we can start working on the actual goal of this. We'll probably start with a character sheet, maybe? The ability to display map? I don't know. I have a README here. Any of these, not multiplayer. Any of these. Any of these, because a token should only be placed on a map. Yep. See you around.